Alright, so good afternoon everyone. So we'll prove the tight cut decomposition theorem today, the unique tight cut decomposition theorem. Technically it should be called uniqueness of the tight cut decomposition theorem. Okay, anyways. So the result, which was proved by Lovász in 1987 in perhaps one of the most iconic papers of the area, matching chord graphs. The paper was titled Matching Structure and the Matching Lattice. You all may recall from the first lecture, the matching lattice is the set of all non-negative, we drop non-negative. It's the set of all integer linear combinations of perfect matchings viewed as 0, 1 vectors. And understanding the matching lattice and characterizing it was a major open problem in the 1970s and 80s. That was solved by Lovász in this paper, the matching structure and the matching lattice. And the first result that Lovász proves in that paper is this. I'll mention a couple of sort of spoilers, but hopefully also create some excitement. So if you assume this result, then you can define some invariants. B of G. B of G is going to be the number of bricks of a matching chord graph G. Right, so you apply the tight cut decomposition procedure and you see how many bricks you get. If you get 2 copies of K4, you count it twice, right? If you get 2 copies of K4, 1 copy of the Peterson graph, and then the rest are braces, then the answer is 3. You got 3 bricks. Yeah. And this will play an important role in some of the things we will discuss in the future. Depending on how much we cover in this course. So this actually appears in various formulas, including the formula of the dimension of the matching lattice. But fun fact, in the dimension of the matching lattice, there is something else that appears. Anyone knows what that is? Well, some of you do, so not you. But any guesses what that is? P of G. Numbers of Peterson bricks. This is going to be the number of Peterson bricks. Yeah, and that also shows up in the formula of the dimension of the matching lattice. So once again showing that the Peterson graph was not just some random discovery, it was very fundamental. Anyways. Okay, so that's just a spoiler. So we will not talk about these things today. Today our goal is to prove the theorem, that these things are actually well defined. In particular, for any 2 applications of the tight cut decomposition procedure, you will get the same list of bricks and braces, right? Up to multiplicities of edges. I forgot to add that. Up to multiplicities of edges. Note that matching chord graph is a brick or a brace if and only if the underlying simple graph is a brick or a brace. Multiple edges don't change the property of being a brick or a brace respectively. Yeah? So that is why you can define the number of bricks and braces as invariants of the graph. Number of Peterson bricks is invariant. Okay, so the first thing that we observed last time is the big problem in this statement is there is a procedure, right? And how do you prove something like this? So one of the first key observations is that you want to throw out the procedure and replace it by something more abstract or convenient. And turns out you can do that. Every application of the tight cut decomposition procedure corresponds to a maximal family of pairwise laminar non-trivial tight cuts of the corresponding graph, and vice versa. And for the vice versa, we also note that the sequence in which you apply the tight cuts doesn't really matter, right? If I give you a family of tight cuts, you can apply them in any sequence you like, you will get exactly the same list of graphs, including multiple edges, including multiplicities. Yeah, everybody agrees with that? Okay, so that's the key point. So therefore, we can now just talk about families instead of procedures. So, well, the proof has essentially started. I won't write proof, it's everywhere. So let script C and script D be maximal families of pairwise laminar non-trivial tight cuts of the graph G. And we are proceeding by induction on order, number of vertices. Right. So the one case we discussed is when these two families have something in common. If their intersection is not the empty set. Okay. So let's just make a quick drawing. This is my graph. I have a cut that is common to both of them. Let's say this cut is F. It belongs to both script C and script D. Then what we'll do is we'll consider the two F contractions. Let F be a common element. We'll consider the two contractions G1 and G2. These are the F contractions of G. Let's make a small drawing of one of them. Let's say this is G1. Okay, so let's say this is my graph G1. Now observe that because this is a family of pairwise laminar cuts, for every other cut in the family, so let's say script C for example, supposing I'm looking at script C, all other cuts basically they look like this. With respect to a given cut, they look like this. Either I draw it here or there, right? And if it is a cut on this side, then it will correspond to a maximal family of pairwise laminar non-trivial tight cuts in G1, where I have shrunken. So this is X, this is X bar. If I shrink X bar to a single vertex, I get G1. So this cut, I will just put it in the family for G1. All the cuts that look like this, I will put them in the family for G1. That will be a maximal family corresponding to G1. And all cuts that look like this, I will put them in G2, where G2 is the other contraction. Yeah. So every cut in my family C or D corresponds to a non-trivial, except for the cut F, of course. Right? The cut F is actually a trivial cut in G1 and also in G2. But every other cut apart from F will correspond to a non-trivial tight cut either in G1 or in G2, but not in both. So using that, I will define the restrictions of C1, C and D to G1 and G2. So I'll get families C1 and D1 for G1 and C2 and D2 for G2. Yeah, everybody agrees? And these are maximal, because if there was any cut I could add, I would have been able to add that cut in the original family. Right? We are using one observation here. Any tight cut in the contraction is a tight cut in the original graph. That is an observation we are using crucially here. Right? So therefore the restrictions of C and D to G1 and G2 respectively are maximal families in those graphs. Yeah? Therefore, because these are smaller graphs, by the induction hypothesis, C1 and D1 are equivalent. Right? Remember, two cuts are equivalent. Yeah, maybe I should write down that point. That's a reminder from last time. We say that script C and script D are equivalent. We will use this notation. If they result in the same list of bricks and braces. Right? So therefore, I'll get two families here, script C1 and script D1, they are equivalent by induction. I'll get two families for G2, C2 and D2, they are equivalent by induction. Well, if C1 and D1 are equivalent and C2 and D2 are equivalent, well then observe that C and D are equivalent, right? Because I can just choose this cut and then I can choose the cuts from C1, then the cuts from C2, doesn't really matter, right? So we are done with this case. Everybody agrees? Yeah? I'll just write down the key points. Script Ci and script Di are restrictions of script C and script D to Gi. And I should define G2. G2 is the same graph where I shrink X to single vertex. Okay. Not great. For I in 1, 2. Observe that also by induction hypothesis, we conclude that C1 is equivalent to D1. I'm applying the induction hypothesis to G1, and C2 is equivalent to D2. Therefore, C and D are equivalent. Yeah. So common cut is great. Great news. Just start with that cut, apply induction, finish off the proof. Yeah. All right. Next case. So last time I wrote not case 1, but this time I'm going to write something slightly different. Supposing there is a cut in script C and a cut in script D, they are not the same, but they are laminar. If they are the same, then we are done by case 1. Okay. So let's suppose there exists a C in script C and a D in script D such that C and D are not the same, however, they are laminar. Sounds better. They are not the same, but they are laminar. Yeah? Okay, well in this case also we are done. Right? This was the TIY I left for last time. So, maybe raise hands if you have a suggestion. Okay, Anjali?
So take a maximal family that contains C and D.
Right.
And that maximal family will have something in common with C and D, and therefore it reduces to
Case 1. Exactly. So what we'll do is, we'll take a maximal family containing these two. These two are not the same, but they are also laminar. So therefore they belong to together C, D is a laminar family. Therefore it can be expanded to a maximal laminar family. Why not? Right? So take a maximal laminar family that contains C and D. Call it script F. Why not? Now observe that script F and script C have something in common. C in particular. So therefore by case 1 they are equivalent. Script D and script F have something in common, D. So again by case 1 they are equivalent. Well, but if two things are equivalent, then you get the point. Equivalence is transitive. Yeah. Okay. So let script F be a maximal family of laminar non-trivial tight cuts containing C and D. Observe that script C is equivalent to script F by case 1, which is also equivalent to script D by case 1, and therefore we are done. Yeah. So case 2 just reduces to case 1. And that is the whole idea of this proof. Observe the most trivial thing, which is case 1 in some sense, and then try to reduce as many things as possible to that trivial case, right? And then see what is left. That is where you need to work hard. Right? Luckily for us, we don't need to. Okay. Questions, concerns so far? All good? Okay. So if either of these case happens, then we are done. Okay. But now let's suppose I pick a cut from C and from D. They are not the same. They are not laminar. Well, they're not laminar. They can't be the same anyways. So therefore they are crossing. Now we need to deal with this case. Okay. Let's call it case 3. I'll move that part here, and you will see why I deliberately kept this empty. So let's suppose we pick a cut from script C, one from script D, and they happen to be crossing. So there exists C in script C and D in script D such that C and D cross. They're not laminar. Okay. So let's make a drawing. Maybe I'll make the drawing here itself. I think this case is clear, right? So okay. So let's make a drawing of two crossing cuts. This is my vertex set. I have a blue cut and a pink cut. This is C, this is X, this is X bar, this is D, this is Y, this is Y bar. Yeah. So for two crossing cuts, I will use the terminology. We will call these the quadrants. Crossing means all four quadrants are non-empty, right? Otherwise they are laminar. Okay, so we know that all four quadrants are non-empty. Let's give them names. Well, the names that are obvious. This is X intersection Y. This is X intersection Y bar. This is X bar intersection Y bar. And this is X bar intersection Y. These are the four quadrants. Some people like to write X intersection Y bar as X minus Y. Very confusing. This is better, uniform. Okay. Yeah? So these are the four quadrants, and these are two crossing cuts. So this is the case we need to now analyze, because we are not done yet. Right? So, okay. So I want you all to think about the parities of these sets. Right? If you already figured it out, good for you. Raise your hand. I'll come and talk to you. Right? So see if you can figure out the parities of these sets, or at least some kind of pattern. Is there some pattern that they follow? And then we'll discuss further. Right? So for example, can all four quadrants be odd? Can all four be even? Right? Remember that the original two cuts are tight cuts. Right? You have to use that fact. Yeah. So I'm not asking about arbitrary crossing cuts. We know that these are tight cuts. Yeah. So use that fact. Yeah, in general, in arbitrary case, you may not be able to say much. So I want you to use the fact that they are tight cuts. Okay. So what can you say about x and x bar? How many vertices in x? Partial x is a tight cut.
Yeah, so it's non-trivial, so
Yeah.
at least 3 of
But
both ends.
can it be even?
In X.
Can x be even? Remember the definition of tight cut. Every perfect matching uses exactly one edge from this cut.
Correct.
So x is?
Odd,
Now use that. You know x and x bar are odd. Y and y bar are odd. Yeah. Yeah. Okay. So we know that x is odd. So both of these can't be even. In fact, one has to be odd and one has to be even. So you might as well adjust notation so that this is odd. That implies this is even. But now y bar is odd, so this has to be odd. And then this has to be even. So you have to see this pattern. If you go clockwise or anti-clockwise, doesn't matter. The parity should alternate. Yeah, okay. So generally we will adjust notation so that these two are going to be odd and these two are going to be even. Yeah? Okay, great. Alright, so that's one point. As I said, the idea is to always try our best to resort to an earlier case. Right? Whenever faced with difficulty, try to find a way to use the easy route. Right? So of course there is some work required, but well, that's where the difficulty will hide. Yeah. So we want to somehow go from this crossing cuts case, we want to somehow go to case 1 or case 2. Well, case 1 is too restrictive. It requires you to have a common element. That may be tricky. Case 2 is a bit more flexible. Okay, it's not common, but at least laminar. So let's see if we can somehow reduce case 3 to case 2. Yeah? Okay? So I claim that we can actually do that.
We don't assume every cut in C and every cut in D are crossing.
No, we are not going to assume that right now. Yeah. Yeah. I mean, so, yes, definitely if you have two cuts that are laminar, you can finish the proof by case 2. Yes, that's true. So you can, if you want, for convenience, you can assume that case 2 does not hold. Therefore, you pick two cuts, they will cross. That is one way to look at it. But later we will see that we don't even need case 2 to not hold. We will just finish case 2, case 3 in a nice way. Yeah. Okay, I'll come to you. so that everybody has some time. Yeah, so anyways, so this is the next DIY. Um, locate a cut maybe let me call it a convenient cut that is laminar with C and or D. Right? So we want to somehow go from this crossing case to the laminar case. Yeah. So can we locate some cut? Of course, it can't be an arbitrary cut. Then you have to prove things about that cut, right? So
C
I'll come. I know I deliberately wrote and or D. Yes, sorry. C and or D. I'll leave that to you. If you have located some candidate cut, then you should try proving that it is a tight cut, right? Because we also need the cuts to be tight cuts. So, part 2. Okay. Anyone else? Okay. Okay. Yeah. Convinced? Okay. Don't give up on the drawing. This is a proof where you have to pay very close attention to the drawing. But you also have to convince yourself that you are not fooled by the drawing. So, this K4 if all the edges are there. Otherwise it is something. Okay? Any idea? Okay, which one? Yeah. Okay. Make use of the drawing. Part 1, candidate cut. No? So you're trying to find a cut that is laminar with the other side. And you want it to be a tight cut, that is part 2. So my point is that there are some natural candidates. Those are the ones you should try out. Yeah. Think about those. Yeah, got it? Okay. So which one? Yeah. Okay. So the natural candidates are exactly these two, right? These two quadrants are odd number of vertices. So consider these two cuts. I'll draw them. We'll call them I and U, because one corresponds to intersection of x and y and the other corresponds to the union of x and y. So this is the cut. I, partial of x intersection y, and this one is U. It is partial of x union y, which is exactly this. Yeah. So these are the two cuts I want you to look at. Clearly they are odd cuts. By odd cut I mean the two shores are odd order, are of odd order. Yeah, they are odd cuts. Of course the even cuts would not be good candidates. They would not be tight. We need a cut to be odd in order to be tight. Now the question is it actually tight? So see if you can think about that. And make use of the drawing. Convince yourself that the drawing is general enough to not fool you. The drawing is as general as life gets. If you have a perfect matching, that uses 3 or more edges from this cut. So that means there are 3 edges that are going to cross the yellow line. Think of this as one line, it doesn't really matter, not geometry. Right? There are going to be 3 edges that cross the yellow line. But that means at least 2 of those 3 cross either the blue line or the pink line. Yeah? If 3 of them cross the yellow line, at least 2 of those 3 must cross the blue line or the pink line. Yeah? Of course, an edge can also cross both lines, like this. This will cross both blue and pink. That's okay. But at least 2 of them will have to cross either blue or pink. But that would contradict the fact that the blue or the pink is a tight cut. Right? So therefore you cannot have 3 or more edges in a perfect matching crossing the yellow line. But it is odd. So therefore every perfect matching meets the cut in exactly 1 edge. Right? You don't have to worry about the case of 2 edges. It's an odd number of vertices that can't happen. Right? Right? So therefore this is a tight cut. I is a tight cut. By symmetry U is a tight cut. Yeah? So I and U are tight cuts. Yeah? And they are laminar naturally to C and D by the choice, by the definition. Yeah? Okay? So let's write down a proposition. 4.12. It's generally called the uncrossing lemma because you had 2 crossing cuts and you were able to somehow get laminar cuts out of that. So you somehow managed to uncross the cuts. Of course, the cuts cannot be uncrossed, they were crossing, but you get the point. It's called the uncrossing lemma. So let's say G is a matching covered graph. C partial X, D partial Y, non-trivial tight cuts. Apparently you can drop non-trivial, but I'm not going to do that. You can think about it yourself. No, yeah. I don't need non-trivial. There are 2 tight cuts. I'm going to assume they are crossing tight cuts. You can drop crossing actually. Even for laminar, you can use the lemma. It is just trivial. The lemma becomes trivial if you make it laminar. Okay, so I'm going to make sure that they're crossing tight cuts. That means all these 4 quadrants are non-empty, and I will adjust notation so that this quadrant is odd. Yeah. Adjust notation so that X intersection Y is odd. If you adjust notation that this is odd, then parities of all the other quadrants are determined. Yeah? Fine. Then, one conclusion that we have already arrived at is that I and U are tight cuts. Then I partial of X intersection Y and U partial of X bar intersection Y bar are both tight cuts. This is the lemma. You have 2 tight cuts, they are crossing. Adjust notation so that the top left quadrant is odd. So you will have odd, even, odd, even. Then the lemma says that these 2 yellow cuts are also tight cuts. Yeah? Everybody's okay with this? Yeah? Okay. And of course, whatever I explained, you can convert that into words. fillet yourself, FIY. Yeah? Okay? Everybody's convinced? We prove this? Yeah? Okay, good. So therefore we have two laminar cuts. They are laminar with each other, but more interestingly they are laminar with the original two cuts. So can we finish the proof from here using case 2? Okay, DIY, and I'll come around. So next DIY. Finish the proof from here. Using case 2. Is good. CMD across it. They are laminar with C, they are laminar with D, but they may be crossing other cuts in the family. That may happen. So we can't conclude that they are in the family. But you can make a new family. Like we did in case 2. In case 2 we made new family. C and let me make it case 1 or 2. Depending on how you think about things, there may be 2 ways to finish it. Case 1 or 2. basically any previous case. If you can reduce to any previous case, just finish it. Let me not. Yeah, thanks.
Even if you use one of them, still there's a catch. So try that also. You use both. You can also use just one of them. You can just use I or U. Try to finish the proof. But even then there's a catch. That's okay. Catch is there for a reason. I also should do some work.
C and I and so case 2 C is
So what did you do?
C and I.
Okay. Then you do another E and I. So then by case 2 C and I. What is G?
C and I.
G is a graph. Okay. Okay. Make it F or something. Otherwise I'm confused. Script F. Okay. So script C and script F are equivalent by case 2. Script N is equivalent to case 2. And these two are equivalent because they both contain I. Yeah. Okay. Sure. That's okay. I think there's a catch. There is a subtle catch, but it is very important. Just want to see it.
Okay. So I think most of you have figured out, probably all of you have figured out, that you basically construct a maximal family. There are many ways to finish this case, but all the ways will have a catch. Okay, that catch needs to be addressed. So let's talk about the catch later. The point is, you take I and C, make a family out of that. You take I and D, make a family out of that. You take I and U, make a family out of that. You do one of these many things, and you somehow reduce to case 1 and case 2. I'll do one such thing. Okay, I don't know which one. Okay, I'll take I and C. Okay, so we'll construct one family containing I and C. They are laminar. They are both tight cuts. Yeah, and they are also not the same. You all agree? I and C are not the same, because all 4 quadrants are non-empty, so definitely I is not equal to C. Yeah, so I can take I and C and make a laminar family containing them. Yeah, similarly I can take I and D and make a laminar family containing them. Let me call one F and H. F contains I and C, H contains I and U. Let me just write down. So F is a maximal laminar family containing I and C, and H is a maximal laminar family containing I and D. Okay, this is one way to finish the thing. Now F and C, script F and script C, have a common element C. Therefore, they are equivalent by case 1. Script H and script D have a common element D, so they are equivalent by case 1 again. But now script F and script H, they also have a common element. or you can take these two to be laminar. You can do multiple ways. So by case 1 and case 2 you can basically finish everything. This is one way. Some of you took a family containing I and U, and then you did something similar and you finished off, right? So all of this is good. But in all of these possibilities, there is a catch. And at least one of you, and maybe more who have seen the proof before maybe, have figured out the catch. So see if you can figure out the catch. So that's the next DIY. Why are we not done? So why are we not done? In every single argument you can come up with, unless you do a lot more work than I've already done, you're basically not done. If you're just using case 1 and case 2, you're not done. So maybe we can take a short break here and continue. So think about the catch, and I also need a break. So we can stop recording and then we'll resume again after the break. Thank you. Alright, so welcome back after the break. And we were here. Why are we not done? Right, and it looks like over the break, pretty much everybody has figured out the reason we may not be done. What if this fellow is trivial? Well, if this fellow is trivial, you go to this fellow. But what if this fellow is also trivial? Then all of this falls apart. So the problem is, when both of these are trivial, we are not done. And sometimes trivial is non-trivial. Right? So this is a good example of that. The problem is, both of these could be trivial. So therefore case 3 is not really case 3, it needs something more. At least one of the two quadrants, one of the two odd quadrants is non-trivial. They cross, and at least one of the two odd quadrants is non-trivial. Yeah? In this case we are done. So case 3, just to be clear, is this. Right? And then you adjust notation so that x intersection y is non-trivial, because we use I. I use I and C, I and D. This argument doesn't go through, because even if one of them is non-trivial, the other one could be trivial. So that is why it is better to use only I, assuming I is non-trivial. So let's say adjust notation. So that I is at least 3. And now the proof finishes. Yeah? So we are done in 3 cases.
I is the correct, not the show.
Oh, I is the, yeah, you're right. I is the, yeah. What I mean is x intersection y, thank you. Yeah, I is the partial of x intersection y, thank you. Yeah, so in this case we are done. So we come to the final case. None of the above cases hold. Alright, this we need to work with. So now we are going to actually use the fact that none of the above cases hold. Yeah. So let's see, I need some space. Let me erase this stuff. Case 4. None of the above cases hold. It's not really above, but anyway, somewhere. Okay, so if none of the cases hold, well, maybe one reason the cases don't hold because both the families are empty. That's just because the graph is a brick or a brace. So, fine. So of course, if C or D is empty, then both have to be empty, right? And the graph is a brick or a brace. Then should actually, yeah, if either of them is empty, then both of them are empty. Then G is simply a brick or a brace, and we are done. Okay, so we can assume that they are non-empty. Yeah. So I'll pick one element from script C, I'll pick one element from script D, and then we'll have to deal with that. Right? So let C be an element in script C and D be an arbitrary element in script D. Because none of the above cases hold, C and D are not the same, they are not laminar, therefore they must be crossing, and the two odd quadrants must both be trivial. Right? Note that C and D cross and both odd quadrants are trivial, also known as singleton. They are both single vertices. Yeah? So, let's suppose we adjust notation so that x intersection y is odd, usual. Let's suppose this vertex is u, this vertex is v. Yeah? Adjust notation so that x intersection y is precisely the element, the set containing u, and x bar intersection y bar is precisely the set containing element v. Maybe instead of the colon here, it should be here. U is a unique element here, and v is a unique element here. These were defined earlier. We are defining u and v now. Yeah? Everybody with me? So far so good? Okay, we need to finish the proof from here. This brings us to, so one possibility is that these are actually singleton sets. So for example, let's suppose, assume, this is an assumption. If the assumption doesn't hold, we still have to deal with that case. Assume that script C is just the cut C and script D is just the cut D. Supposing this happens. Let's look at a concrete example where this happens, right? The smallest graph where this happens, we have already seen it. This is a graph where this happens. To make it more interesting, you put a parallel edge here. Then the two contractions are actually going to be not the same. So what could happen is, maybe the C, the blue cut, maybe it's this one. And maybe the pink cut is this one. This graph has only two non-trivial tight cuts. So in this graph, if you take two maximal families, there will be exactly these two. One will contain the blue cut, one will contain the pink cut. And that is this situation. And the two odd quadrants are indeed trivial. These are your U and V. Right? You can't resort to any of the previous cases in this. You have to deal with this case. How can you go to any of the previous cases? Absolutely no way. Right? Every induction proof has to have some non-triviality somewhere. If you see no non-triviality anywhere, probably the proof is wrong. Like the standard example, all horses are black. If you have seen this, right? Anybody has seen a proof of this? All horses in the world are black. Have you seen this one? It's the standard induction paradox. Okay, I teach it in discrete math. So maybe. So one way to prove that all horses are black, if there is only one horse in the world, no, not black. All horses are of the same color, not black. All horses are of the same color. So how do you prove this? If there's only one horse, of course it is of the same color. I mean, what? Right? If there are lots of horses, you take two sets. All of these are of the same color. All of these are of the same color. But they have a common intersection, so they are all of the same color. But this proof fails somewhere. This argument fails in the case of two. If there are only two horses, then this fails. And so you have to show that two horses are the same color, which is equivalent to saying all horses are the same color. Right? Anyway, so if your induction proof has no non-triviality anywhere, you should be worried. So this is where the non-triviality is. Right? Okay? Good. So we'll have to deal with this case. But before we deal with this case, I want to go to the TIY I posted on Piazza. I want to discuss that. Right. So that TIY is a slightly more general setting. I think we all know the theorem we are trying to prove, so I think we can skip the theorem statement now. Okay. So here is the TIY I posted yesterday. So we have two cuts. They are crossing cuts. We are going to assume they are bonds actually. I'm going to assume I have a connected graph and I have two bonds. So this is C, x bar, d y bar. I don't know anything about parity. It's just a connected graph and these are two crossing bonds. Okay? G is a connected graph and C and D are two crossing bonds. Then I want to compare two graphs. Okay, here I'm not assuming anything about the shores being trivial, non-trivial, nothing. Okay, yeah, they are crossing. So all, of course, all quadrants are non-empty. That is clear. Okay, and now I want to compare two graphs. The first graph is going to be, I'm going to keep this part as it is. First I will shrink x into single vertex. I'll shrink x into single vertex, and then I'll shrink this fellow, x bar intersection y bar into single vertex. And the second graph, I will first shrink y bar into single vertex. And then I will shrink this fellow into single vertex, x intersection y. Yeah? And I want you to think about what is the difference between these two graphs. And hopefully you made an example where they are actually non-isomorphic. Not only are the graphs non-isomorphic, the underlying simple graphs are also non-isomorphic. Right? So let's look at an example. In which the underlying simple graphs of these two are non-isomorphic. Yeah? Did everybody work this out? Anybody tried this? No? Nobody? You tried it? Okay. Anyone else tried it? No? Nobody tried it? Okay, so you have an example?
Yeah, I tried one.
Okay, draw it. Okay. Sorry?
Example is big.
Example is big. Oh, you want more space? Or you can use this space also. It's slightly bigger. It's narrower.
So I'll tell the idea. We know T6. So basically I took T6.
T6 is this graph without the parallel edge. That's
Without
T6.
parallel edge,
Yeah.
and I splice this vertex with another vertex of T6, like one more copy of T6 here, T6 here,
Oh wow.
K4 here, K4 here, and consider similar cuts. That's the example.
Okay.
So if you want me to draw it,
So you splice T6 here.
huh,
You splice
copy of T6 here, copy of T6 here,
copy of T6 here.
K4 here,
K4 here. And that's it?
that's it, and keep the cuts like
The cuts are the same?
Huh.
Seems strange. You got non-isomorphic even after taking the underlying simple graphs. Can you check it again?
Yeah.
Yeah, just check it again. I'm not convinced that that will work. Yeah, so it's a big example. So see if you can check it again. My understanding is that you should add some edges, otherwise it shouldn't work. Unless I'm missing something. So maybe the TIY I gave is incorrect. Of course, I did not even spell out the entire TIY. I asked you to figure it out. The online audience must be bored to death. Hopefully they are also trying to figure out. It's like, there's too much silence. let's make some observations. Because both of these are bonds. So there are 6 types of edges here, depending on the 4 quadrants. 1, 2, 3, 4, 5 and 6. Yeah. Which edges can we say definitely exist? Call them type 1, type 2, type 3, type 4 and type 5 and type 6. Which edges definitely exist? Which types definitely exist? Because these are bonds.
From
From
x bar intersection y to
x bar intersection y to from here, from this quadrant, there should be an edge going to which quadrant? Which one? The next one here. This kind of edge must exist. Right? It's a bond. So both shows induce connected subgraphs. Right? SGT. By the same argument, this must exist. Some edge of this type must exist. Some edge of this type must exist. Some edge of this type must exist. The other 2 types we can't tell. They may or may not exist. And that is what this is related to. So you want the 2 graphs to be non-isomorphic. The underlying simple graphs, you want them to be non-isomorphic. You want to make an example where that happens. Yeah. You have an example? Okay, how many vertices? 12. Okay. Come over. Huh? You want to tell me the example? Okay. Okay. C3. C4 separately? Here? Here? Path of 3 vertices. Here? Zero, 7, 2, 7. 8 to 3. 0 to 4.
Then 10 to 5 and 6.
10 to 5 and 6.
Also 0 to 9.
0 to 9.
Eight to 9.
8 to 9. Yeah. And what are your cuts? Tell me the shore of one cut.
So one cut is the C3 and K2.
C3 and K2. And is the other cut like this?
No, it's the 2 cycles.
The 2 cycles, that is another cut. Okay, fine. The 2 cycles. Yeah? Is that correct? Okay, now draw the contractions. And observe that they are not isomorphic. The underlying simple graphs are not isomorphic. I'm not going to draw it. You all can do it. I drew enough. So I'll label the things. One of C is going to be x and x bar. So this is your x and x bar. And this pink set is y. And outside the pink set is y bar. Okay? You have two choices. Either draw or make a smaller example. I don't know. I did not make the smallest example. I'm assuming the statement is correct. You can actually make a counter example. But yeah, the smaller the better. So why exactly are we doing this? Right, so we are in this case. Where is the case? Case 4. This is the case we are in. This is an example of this case. And in this example, we want to observe that for the two graphs, basically for the two C contractions, should be isomorphic to the two D contractions up to multiplicities of edges. So at least the underlying simple graphs for the C contractions should be the same as the D contractions. Of course, observe that here, two of the shores are already trivial. Here I am not making that assumption. Here I am allowing all the shores, I am allowing them to be non-trivial. Of course, they could also be trivial, they are non-empty. So what we are trying to do here is we are trying to observe something more general. Right? So this TIY was designed as an exercise that is much more general than this specific setting.
I have a simpler example.
You have a simpler example?
8 cycle
Okay.
with 2 edges.
8 cycle with 2 edges, that's it.
2 additional.
Oh, good. I'll make that.
I have one.
8 cycle with 2 edges.
Zero, 4 and 1, 5.
0, 4,
1, 5.
1, 5.
Cuts are vertical and
Cuts are
vertical and
vertical and horizontal. Excellent. Blue and pink. What is the, so the horizontal is like this? Okay, so let me see. Horizontal is blue, like this. And this is the pink cut. This works? Okay? Try this out. No need to try the other one now. Draw the two C contractions. No, not C contractions. You get the point. Let me label them. So X bar and Y bar. Draw these two graphs. If anybody would like to come and draw the contractions, feel free to come here.
This is a smaller example.
Smaller example? Okay, but this one works? Did you check it? No, but you have a smaller one. How many vertices?
5.
5 vertices. 5. You want to draw it? Okay. I'll make space for 5 vertices.
You can also skip one contraction because one of them is going to be trivial.
Sorry?
One of them is going to be trivial, so
Okay.
there's only one step.
Okay. Okay, so you can get the two chalks there. Okay, cool, thank you. Maybe everybody can try this also. Now we have multiple examples. Yeah, works. Or did I label things correctly or did I label things incorrectly?
Yes.
Labeling is okay of x bar, y bar,
Yeah.
because the things may matter actually.
Yes. Yeah, that's right.
It's correct?
Correct, yes.
Should be swapped, right? Can you check again carefully?
Okay.
Are you following my notational convention or are you following your convention? Should be changed?
No, it's, I mean, works for me.
No, it's fine. It's fine. It's fine.
It's fine? Okay, fine. Yeah, let me check. Okay, it's fine. Yeah, it's fine. Yeah, I mean, yeah. Okay, so can everybody check that these two are not the same graphs for this example? And if you have enough time also for this one, this is not too big, it's very symmetric actually. Yeah, try it out. Yeah, you don't get the same graphs. Even the underlying simple graphs are non-isomorphic. So why is the non-isomorphism happening? What are the types of edges that matter? If you have figured it out, let me know and I'll come and talk to you.